Welcome everyone. We will be continuing with trigonometric integrals. Before talking about equations that we will need, I want to remind that, or we want to see that, which trigonometric integrals we can solve so far. For example, integral of sine of x dx is equal to cosine of x plus c, because negative cosine of x plus c, because when you differentiate this, it gives you sine of x. Or integral of cosine of x dx is equal to sine of x plus c. Or integral of cosine of 5x dx is equal to negative sine of 5x over 5 plus c. Because I'm asking myself which function, when I differentiate it, gives me the integrand, this part. And that is my answer, obviously. But what if I ask you the question, what is the integral of sine squared x dx? You have to come up with a function and you differentiate it, it gives you sine squared of x. It is not that obvious, so we will need some equations to solve this integral. Our first equation, cosine of 2x is equal to 1 minus 2 sine squared x. This is an equation you probably learned in high school. And from this equation, sine squared x is equal to 1 minus cosine of 2x over 2. If you leave the sine squared x from here by itself. And the other one, or let's say, now instead of this integral, I will just solve 1 minus cosine of 2x over 2 dx. And you can simply separate this, right? 1 of dx minus cosine of 2x over 2 dx. And you can do some more work with this, like this, integral dx minus integral cosine of 2x dx. Now you have two separate integrals, and these integrals are really easy to solve. This is the idea behind using this equation. And for the, do I have enough space? Not really. Okay, then let's clean a little bit. And if I want to integrate cosine squared x dx, cosine of 2x is equal to 2 cosine squared x minus 1. And if you leave the cosine squared x alone, you get this equation. These two equations we learned it in our previous classes as well, but you will use it in this one as well. 1 plus tan squared x is equal to secant squared x, and 1 plus cot squared x is equal to cosecant squared x. All right, now let's see some simple integrations related to what we learned so far. Integral of sine squared of ax dx. What does ax mean? A is any real number, right? 2, 1, 2, 2 over 3, doesn't matter. All right. The issue is, what I know is cosine of 2x is equal to 1 minus 2 sine squared x, which gives me sine squared x is equal to 1 minus cosine of 2x over 2, right? Yes, exactly. Now, I have sine squared of ax, not sine squared of x. Therefore, instead of this, there's a hidden one here, which is multiplied with 2 here, so therefore this will be 1 minus cosine of 2ax over 2. Let's integrate this now. 1 minus cosine of 2ax over 2 dx, which is equal to integral 1 half dx minus integral cosine of 2ax over 2 dx, which can also be written as 1 half multiplied integral of dx minus integral of cosine of 2ax dx. The question is, what is the integral of cosine of 2ax? I know that cosine of x integrated is sine of x dx. So integral of cosine 2ax dx will be sine of inside of it 2ax. When you differentiate the inside, 2a. So if I differentiate this function, I multiply with 2a. Therefore, I need to divide with 2a. Good. Now, if I just write this, as the solution of my integral. 1/2 integral of dx is x minus sine of 2ax over 2a. There's a plus c, and this can be written as x minus sine, or let's just leave it x over 2 minus sine of 2ax over 4a plus c. Now, I will skip to the integral of tan squared of ax dx because you can do the same for integral of cosine squared a of x dx. I want you to solve this by yourself. How are you going to do it? Instead of cosine squared ax, you will write using this equation, this part of it. This part is this part is what you need. This is trying to show me, like this is me trying to show you guys how to drive the formula. This is going to be 1 plus cosine of 2ax over 2 dx. You just need to do the same thing. You need to separate this into two different integrals and solve it from there. All right. Now, integral of tan squared of ax dx. This is where I need to use my other equation, which is 1 plus, as we know, tan squared x. 1 plus tan squared x is equal to secant squared x. But the issue is I have an ax, therefore this will be, I feel like I'm taking too much space. I don't like that. So this will be 1 plus tan squared ax is equal to secant squared ax. From here, tan squared ax is equal to secant squared of ax minus 1. I will integrate this instead of the tan squared ax. Now our integral becomes secant squared of ax minus 1 dx. Separate this into two different integrals. Integral of secant squared of ax dx. I didn't need to add the parentheses. Dx minus integral of dx. Again, I have to ask myself the question, what is the integral of secant squared of ax? Integral of secant squared x dx is equal to tan x plus c, because differentiating tan x gives me secant squared x. So therefore, integral of secant squared ax dx will be tan of ax, tangent of ax, plus c. Of course, this is over a, because first you differentiate outside and then inside there's an extra a, so you need to divide with it. Therefore, the answer is tan of ax over a minus x plus c. Our third example, integral of secant of ax dx. Now, this is kind of a special integration. There are two methods to solve this. I will show the easier one, slightly easier, I guess. Okay, so first thing, if you will do a substitution, a u substitution, u is equal to ax. Therefore, du is going to be a dx. And therefore, dx is going to be 1 over a du. Now, this integral becomes, let's see, u. So this is 1 over a integral secant of u du. How do we solve this integral? What I want you to do is just learn the thing I'm going to do, because you will see why it works later on. Just follow the steps. Let's focus on integral of secant u du. I want you to multiply this inside of the integral with secant u plus tan u over secant u plus tan u. I did not change anything because this is equal to 1. You might ask, why did you do this? Let's see why I did it. Now if I multiply the secant u, let's distribute. Secant squared u plus secant u times tan u. This is over secant u plus tan u du. There's a trick in this integral now. It's really hard to see, but if I do another substitution, let's say z is equal to the denominator, so secant u plus tan u. And when I differentiate both sides, dz is equal to secant u times tan u when I differentiate secant plus when I differentiate tan u, which gives secant squared u du. This is equal to exactly my numerator. So instead of du, now I can write integral of the denominator is z, secant squared u plus secant u tan u times, instead of du, dz over secant squared u plus secant u tangent u. I can cancel these out. This integral is 1 over z dz, which is easy to solve, ln absolute value of c plus c. What is z? Z is equal to secant u plus tangent u, so ln absolute value of secant u plus tan u plus c, but it's not over because u is also a substitution, which is equal to ax, and we should not forget 1 over a, so this is equal to 1a, 1 over a. Let's say I, which is my integral, is equal to 1 over a ln absolute value of secant of ax plus tangent of ax plus c. Okay, that was our last example. Or maybe I can show how to integrate cosecant of ax dx. Okay, if you learned anything from this integration, you will kind of understand that we will do the same thing. Ax is going to be u, du is going to be a dx, and dx is going to be 1 over a du. Again, this becomes 1 over a integral cosecant of u du. I will multiply this with, and now again, let's focus on cosecant u du. I will multiply this with cosecant u plus, this time, of course, cotangent u, because again, it will be the same thing when I call the numerator, denominator z. I use a substitution. It will give the same thing. I mean, it will give the numerator. And this becomes integral of cosecant squared u plus cosecant u times cotangent u. This is over cosecant u plus cotangent u du. Z is equal to denominator cosecant u plus cotangent u. And dz becomes, now you have to be careful because there will be minus signs here, which will give us negative cosecant u times cotangent u. In the differentiating the cotangent u gives us negative cosecant squared u. This can be written as, of course, there's a du as well, du. And I can write this as negative cosecant u times cotangent u plus cosecant squared u du. And again, you will see that this part, this differentiated function, is exactly the same with the numerator. So this becomes cosecant squared u plus cosecant u times cotangent u This is over z times negative sign. I will take the negative sign out of the integral. Mm, dz over cosecant u times cotangent u plus cosecant squared u. These terms will cancel each out. And now I'm left with integral. Well, I can just write the answer at this point. Ln absolute value of z plus c. And now writing back the substitutions. There's a 1 over a ln absolute value of cosecant u, but this is ax as well. So cosecant of ax plus cot of ax plus c. As I said, it's the same solution with the secant of x or ax, doesn't really matter. The reason I added these a's is because I wanted to show you can use this method to like any real number. You don't need to integrate secant 2x, secant 3x, secant of 4x. Like you can just do it for any real number. And one more thing is I didn't solve it, but as I said, you can integrate cosine squared of ax with this equation. And for the cot squared x, you have to do the same thing that we did for the tan squared of ax. You just need to follow the same steps. Instead of course, you will not use this equation, you will use this equation.